Okay, so today we're going to talk about volume, finding the volume of a three-dimensional figure or a solid is what it's typically called, by known cross sections. So the idea here is this: when we are considering finding a volume, much like when we did the disk method or the washer method, we will start with some region. So in this case, the region itself is the area between this top red curve here and this bottom blue curve there. The equation of the function doesn't really matter for what I'm trying to demonstrate today. I just want to talk about the concept of what we're going to be dealing with. So imagine this region here. And different than volume by revolution, we are not going to take this region and revolve it around a line. If we did, depending on what we revolved it around, it would be either a disk or a washer. Each slice would be, some sort of cylinder. You find the volume of that cylinder, and you stack that up or integrate that from, either a x value to an x value if you're revolving around a horizontal line, or from a y value to a y value if you're revolving around a vertical line. What's different about volume by cross section is, imagine this region to be the base of your solid. What that means is the base is always going to be flat. So we're not going to be revolving around a line which creates a three-dimensional figure in space. Instead, this region is now going to be the base of the solid. So this video is meant to demonstrate the concept here. So imagine taking this region and laying it flat. So the easiest way to show you that is over here. Again, this purple line is going to represent one of the cross sections, and I'll show you what that means in a second. So imagine taking this and laying it flat. So I'm just kind of tilting it away from me, and imagine this is the base of the solid. Now I'm going to tilt it a little bit back up a little bit so you can see it, but that's kind of what we're looking at. So this is the easiest way to see it. So imagine this region is now the base, so flat. And what's going to create this three-dimensional solid is a specific shaped cross-section. So here we have three different options. There are more than that. So square, triangle, semicircle. Could also be given a rectangle, a different type of triangle, a bunch of different shapes, but they're all geometric shapes that we know. So imagine, let's start with something that's pretty straightforward, a square. So if I were to go back to this two-dimensional view from the top, you can't really tell what this is, but what you have to imagine is this is a square. So the base of the square is the distance from the top function to the bottom function, or top minus bottom, and the height of it, and again, laying it flat is the easiest way to demonstrate that, the height of it, so the base is here, the height is there, should be exactly the same. So whatever this base is the same as this height. So imagine this three-dimensional figure is going to be made up by a bunch of these square cross sections. So I can do that by, I'm going to leave x to be a half, and what that is kind of where this upper bound is. But if I start filling in this region with more and more squares, you can see how it starts to create a three-dimensional solid. So again, I'm going to go all the way, this goes all the way up to 100. So imagine this is what the shape of your solid is. And I can tilt it around and you can kind of see what it looks like. But what's different is the base of this is still flat. We didn't revolve around the line. It's still a flat base, but each slice of this would be a square. So how would I find the volume of this figure? Well, if you consider finding the volume of one slice being a square with a very small depth. So imagine, I'm going to kind of turn it sideways. You can see that this square, imagine it is very, very thin. So we'd call this depth, dx, some very small change in x. So the base, we should know. The base would be the distance from top curve minus bottom curve. The height should be exactly the same as the base, which is what makes it a square. So the way you'd find the volume in these types of problems would be find the volume of each slice and integrate it from, in this case, maybe 0 to a half, or I can make that upper bound all the way at 1. And again, if I start filling it in with squares, you can see how it forms this three-dimensional figure. So I'm going to back it up so you can kind of see what's happening. We're just going to be considering one slice. And let's put that slice kind of somewhere in the middle so we can visualize it. If I find the volume of the slice, which would be the area of the square times the depth of the square, which we're going to call in this case a very small change in x, and I integrate that from, in this case, 0 to a half, that would be my volume. Now, what could change in this case? Obviously, we could change the shape of the region or the location of the region. We could also change the shape of the slice. So imagine instead of a square, we looked at a semicircle. So if I found the volume of this semicircle, which would be the area of a semicircle times a very small depth, or in this case dx, and I stacked them up from, in this case, 0 to a half, I would be finding the volume of this region. Here's what this one would look like. Same base, but now I'm filling it in with semicircles. It would look something like that. And we're going to find the volume of that by considering the volume of one individual slice stacked up from a lower bound to an upper bound to kind of fill in this entire region. So that's what it would look like for a semicircle. Let me back it up to be 1 again. What would it look like for an equilateral triangle? So again, this is what you would normally see. Here's the two-dimensional view. If I were to lay this region down, I'm going to put a little tilt on it so you can see the triangle itself. We'd have a bunch of equilateral triangles sticking directly out at us. That's what this view is over here. Equilateral triangle sticking straight out at us. This is what it would look like. Now, if I filled in this region with a bunch of equilateral triangles, you can see the base is still the same. The functions are still the same, but if I were to kind of turn it, you can see that this three-dimensional figure is made up of a bunch of equilateral triangles. So major concept is we're not revolving anything. We are going to be finding the volume of individual slices, depending on the shape that we're told, in this case equilateral triangle, and we are going to be stacking them up from somewhere to somewhere, and what it does is create a three-dimensional solid. So what I'm going to do, to the best of my ability, is draw the picture like this in 2D, put a line there to represent the slice, and then I'm going to try my best to draw this y-axis and this x-axis in the region and kind of draw this slice sticking out at us. Now, I'm limited in my capacity. Technology does it way better, which is why I'm making this video. But I'm going to do my best to draw a couple slices so you can kind of see. I might draw something that looks like that. So you can kind of see there's a couple different triangles formed. And if we find the volume of each one and stack them up, we'd be integrating and finding the volume of the entire region.